You've felt speed before. Perhaps you've pressed the accelerator on an empty highway and watched the needle climb past numbers that made your heart beat faster. Perhaps you've sat in the window seat of an airplane and watched the ground blur beneath you at 500 miles per hour, cities and mountains reduced to smears of color, sliding past like images in a dream. Perhaps you've ridden a roller coaster that pressed you into your seat with a force that squeezed the breath from your lungs, the world spinning around you in a chaos of motion and adrenaline. Speed is something your body understands at a primal level, something written into your nervous system through millions of years of evolution. The wind against your face, the blur of scenery rushing past, the pressure in your chest as acceleration pushes you backward, these sensations are among the most visceral experiences a human being can have. We are creatures who understand speed instinctively, who can feel the difference between walking and running, between a gentle breeze and a howling gale. But tonight, we're going to explore speeds so extreme that they will break every intuition you have about what it means for something to move fast. We're going to climb a ladder of velocities that stretches from the familiar to the incomprehensible, from the pace of a casual stroll to speeds where time itself begins to warp and bend. By the end of this journey, the fastest thing you've ever experienced will seem frozen in place, as motionless as a statue, compared to objects that race through the cosmos at velocities that approach the fundamental speed limit of the universe itself. Let's begin with something so familiar you probably don't think of it as speed at all: walking. The average human walks at about 3 to 4 miles per hour. This is the pace your ancestors maintained as they crossed continents over thousands of generations, the speed at which humanity spread across the globe before we invented wheels or domesticated horses. At walking speed, you could cross the United States in about 6 to 8 months of continuous travel, assuming you never stopped to sleep or eat, or rest your aching feet. This seems slow by modern standards, almost comically so, but for most of human history, this was the fastest most people ever traveled. Walking speed shaped the geography of civilization itself, determining how far apart villages could be while still allowing trade and communication, establishing the natural radius of human communities before the age of machines. Your brain evolved to understand this speed, to track objects moving at this pace, to judge distances based on how long they would take to traverse on foot. 3 miles per hour is the speed of human existence, the baseline from which we measure all other motion. Running pushes us faster, but not by as much as you might think. The fastest human being ever recorded, Usain Bolt, at the peak of his legendary 100-meter sprint, reached a speed of about 28 miles per hour. He maintained this pace for only a few seconds, his muscles burning with the effort of pushing his body to its absolute mechanical limit. At this speed, you could cross a football field in about 8 seconds, the world blurring at the edges of your vision as every fiber of your being strained toward maximum velocity. This is the upper boundary of human locomotion, the fastest any person has ever moved under their own power without the aid of machines or gravity. 28 miles per hour. It sounds impressive until you realize that a cheetah can sustain 70 miles per hour, that a peregrine falcon can dive at over 200 miles per hour, that even among biological creatures, humans are not particularly fast. We conquered the world not through speed, but through endurance and intelligence, through our ability to outlast prey over long distances and to build tools that extended our capabilities far beyond what our bodies could achieve alone. And it is those tools, those machines, that first allowed us to break free from the limitations of muscle and bone. The age of machines transformed human speed in ways our ancestors could never have imagined. The first automobiles of the 1880s could barely exceed walking pace, sputtering and coughing their way down rutted roads at speeds that horses easily matched. But within decades, cars were traveling at 60 miles per hour, then 100, then faster still. The current land speed record stands at 763 miles per hour, faster than the speed of sound, achieved by a jet-powered car that crossed the Black Rock Desert in Nevada in 1997. The driver of that vehicle experienced forces that would have been instantly fatal to an untrained person. His body pressed into the seat by acceleration that pushed against the limits of human endurance. 763 miles per hour, is fast enough to cross the Atlantic Ocean in about 4 hours, fast enough to feel like genuine speed, even by the standards of our accelerated modern world. And yet, compared to what aircraft can achieve, even this record-breaking car is almost leisurely. Commercial jetliners cruise at about 500 to 600 miles per hour, carrying passengers across continents and oceans in journeys that once took months by ship. The remarkable thing about flying at this speed is how ordinary it feels. You sit in your seat, perhaps reading a book or watching a movie, while outside your window, the Earth slides past at a pace that would have seemed like magic to anyone born before the 20th century. Speed has become invisible, normalized, mundane, but military aircraft push far beyond these commercial limits. The SR-71 Blackbird, the fastest air-breathing crewed aircraft ever built, could travel at over 2,000 miles per hour, more than 3 times the speed of sound. At this velocity, the aircraft didn't evade enemy missiles so much as simply outrun them, leaving threats behind in its wake as it streaked across the sky faster than anything else with a human pilot aboard. The Blackbird could cross the continental United States in about 67 minutes, coast to coast in little more than an hour, covering distances that wagon trains once measured in months. Beyond even the Blackbird lies the X-15, a rocket-powered aircraft that reached 4,500 miles per hour in the 1960s, carrying test pilots to the edge of space and back. At this speed, you could travel from New York to Los Angeles in about half an hour. The pilots who flew the X-15 experienced weightlessness at the peaks of their trajectories, their craft arcing so high that they technically qualified as astronauts, touching the boundary where atmosphere gives way to the vacuum of space. But even the X-15, that marvel of human engineering and courage, represents only a fraction of what machines can achieve when we remove the fragile human body from the equation entirely. The Parker Solar Probe, currently the fastest human-made object ever constructed, will reach speeds of 430,000 miles per hour as it swings close to the Sun, using our star's enormous gravity as a cosmic accelerator. At this speed, you could travel from Earth to the Moon in about 30 minutes, from New York to Los Angeles in roughly 20 seconds. This is the pinnacle of human speed, the fastest we have ever propelled any object through space. And compared to what the universe itself can achieve, it is barely moving at all. To truly appreciate the speeds we're about to explore, we need to understand just how far human technology has brought us from our walking ancestors, and how far we still have to go before we approach anything resembling cosmic velocity. The history of human speed is a story of constant acceleration, each generation surpassing the previous in ways that would have seemed impossible just decades before. When the first steam locomotives began chugging across the English countryside in the early 1800s, some physicians warned that traveling at 30 miles per hour might cause passengers to suffocate, their lungs unable to function at such unnatural velocities. The human body, these doctors insisted, was simply not designed for such speeds. Within a century, their grandchildren were flying across the Atlantic at hundreds of miles per hour, and within another century, astronauts were orbiting the Earth at 17,000 miles per hour, circling the entire planet in about 90 minutes. Each threshold that once seemed like an absolute limit turned out to be merely a stepping stone to the next level of velocity. The sound barrier represents one of the most famous of these thresholds. Sound travels through air at about 767 miles per hour at sea level, a speed that seems almost instantaneous in everyday experience. When you clap your hands, the sound reaches your ears so quickly that you perceive it as immediate. When you see lightning in the distance, the thunder follows seconds later, the gap between flash and boom revealing the finite speed of sound across miles of atmosphere. For most of human history, this speed was considered extremely fast, far beyond anything humans could achieve. When aircraft began approaching the sound barrier in the 1940s, engineers worried that the laws of aerodynamics would prevent anything from flying faster. The air itself would become an impenetrable wall, they feared, destroying any craft that attempted to breach it. Pilots reported severe turbulence and loss of control as they approached this invisible boundary, their aircraft shaking violently as shockwaves built up around the wings and fuselage. Some planes did disintegrate, their structures torn apart by forces they were never designed to withstand. But on October 14, 1947, a test pilot named Chuck Yeager climbed into a small orange rocket plane called the Bell X-1 and proved that the sound barrier could be broken. His aircraft was dropped from the belly of a bomber at high altitude, and as its rocket engine ignited and pushed him faster and faster, Yeager felt the familiar buffeting that had terrified other pilots. And then, as he crossed the threshold into supersonic flight, something remarkable happened. The turbulence vanished. The ride became smooth. He had punched through the invisible wall and emerged on the other side, traveling faster than sound itself, faster than the thunder his passage was creating behind him. The sonic boom that rolled across the Mojave Desert that day announced a new era in human speed. What had seemed impossible had proven merely difficult. The barrier was not a wall but a door, and we had learned to open it. Since Yeager's flight, humans have pushed far beyond the speed of sound, reaching velocities that make his supersonic achievement seem almost quaint. The space shuttle re-entered Earth's atmosphere at about 17,500 miles per hour, enduring temperatures that would melt steel as air friction converted its tremendous kinetic energy into heat. The astronauts inside experienced this as a prolonged period of deceleration, pressed into their seats as the atmosphere gradually slowed their craft from orbital velocity to landing speed. The Apollo astronauts traveled even faster, reaching about 25,000 miles per hour on their journeys to the moon, the fastest any human beings have ever traveled. At this speed, you could circumnavigate the Earth in about an hour, crossing continents and oceans in the time it takes to watch a television episode. The astronauts of Apollo felt this speed in their bones as they accelerated away from Earth. The crushing force of the Saturn V rocket's thrust, pressing them deep into their couches as the most powerful machine ever built, hurled them toward the moon at velocities no human had ever before achieved. But even these incredible speeds pale against what we can achieve when we remove the delicate human body from the equation. Robotic spacecraft, unburdened by the need to keep fragile biological passengers alive, can withstand accelerations and velocities that would instantly kill any astronaut. The Voyager probes, launched in 1977, travel through interstellar space at about 38,000 miles per hour, a speed they will maintain essentially forever as they coast through the void between stars. They are the most distant human-made objects in existence, now more than 14 billion miles from Earth. Yet even at their impressive velocity, they would need tens of thousands of years to reach even the nearest star. The New Horizons spacecraft, which gave us our first close-up images of Pluto, traveled at about 36,000 miles per hour during its journey through the outer solar system. The Parker Solar Probe will eventually exceed both of these, using repeated gravity assists from Venus to swing ever closer to the Sun, trading distance for velocity, as it falls deeper into our star's gravitational well. There is something profound about the way gravity can accelerate objects to such tremendous speeds. The Sun contains 99.8% of all the mass in our solar system, and anything that falls toward it gains velocity at a rate that dwarfs what any rocket engine can achieve. The Parker Solar Probe is essentially falling toward the Sun in a carefully controlled manner, using the same force that pulls an apple from a tree to accelerate itself to nearly 500,000 miles per hour. This is clever engineering, using the natural structure of the solar system as a cosmic accelerator far more powerful than anything we could build. And yet, even this achievement, remarkable as it is, barely scratches the surface of what natural acceleration can accomplish. The universe has been accelerating objects for billions of years, using forces and mechanisms that dwarf anything in our solar system. Gravity wells deeper than our sun, magnetic fields stretched across light years, shock waves from exploding stars. These cosmic engines have been pushing particles and objects to speeds that make our fastest spacecraft look like they're standing still. The gap between human speed and cosmic speed is almost impossible to grasp. The Parker Solar Probe, traveling at 430,000 miles per hour, is moving at about 0.06% of the speed of light. To go from our fastest spacecraft to the fastest objects in the universe requires an increase in velocity by a factor of more than 1 million. Every increment of human progress, from walking to running to driving to flying to rocketing through space, all of it together represents only the tiniest first step on the ladder of cosmic speed. We have climbed from the ground floor to the second floor and convinced ourselves we are making progress toward the top of a building with millions of stories. The humility this comparison should inspire is not meant to diminish human achievement, but to properly frame what the universe is capable of. We have done remarkable things in our few centuries of technological development, but the cosmos has been doing far more remarkable things for far longer. And the speeds it has achieved make everything humanity has ever accomplished look like a rounding error in the great equation of motion and velocity. Long before humans built machines that could travel faster than sound, nature was demonstrating speeds that dwarfed anything our ancestors could achieve. The natural world is filled with phenomena that move at velocities we can barely perceive. Events that happen so quickly they appear instantaneous to human senses. Forces that cross vast distances in the blink of an eye. Understanding these natural speeds helps us appreciate the ladder we're climbing, each rung representing another order of magnitude beyond what came before, each step preparing us for the cosmic velocities that await at the top. The speed of sound, which once seemed like an insurmountable barrier to human flight, turns out to be almost leisurely compared to other phenomena occurring all around us every day. Sound waves propagate through air at about 767 miles per hour at sea level, a speed that varies with temperature and pressure, but remains roughly constant under normal conditions. This is why you see lightning before you hear thunder, why fireworks bloom in silence before their booms reach your ears, why a distant baseball player swings his bat in apparent quiet before the crack of contact arrives at your seat in the stands. Sound is fast by human standards, crossing a football field in about a third of a second, but it is remarkably slow compared to other forms of energy transmission. Light, for comparison, travels nearly 1,000,000 times faster than sound. When lightning flashes across the sky, the light reaches your eyes essentially instantaneously, while the thunder it creates takes about 5 seconds to travel each mile between you and the strike. This difference allows you to estimate how far away a thunderstorm is simply by counting the seconds between flash and boom. But lightning itself, that brilliant discharge of electrical energy arcing between cloud and ground, demonstrates speeds far beyond what sound can achieve. The visible lightning stroke, the leader that reaches down from the cloud, travels at about 270,000 miles per hour. This seems incredibly fast, and it is, but the return stroke that follows, the brilliant flash that illuminates the entire sky, moves at roughly 1/3 the speed of light, 220 million miles per hour, give or take, racing from ground to cloud in a fraction of a microsecond. This is why lightning appears instantaneous, even though it's actually a complex sequence of events unfolding at different velocities. The return stroke is one of the fastest naturally occurring phenomena on Earth's surface, a reminder that the speeds we're exploring exist not just in distant space, but right here in our atmosphere, in storms we've watched since childhood. Electrical signals in general travel at remarkable speeds, which is why our modern world of instantaneous communication is possible. When you flip a light switch, the electromagnetic wave that carries the signal to the bulb travels at about 90% of light speed through copper wire, roughly 180 million miles per hour. The electrons themselves move quite slowly, drifting through the wire at only inches per hour, but the wave of electromagnetic influence that pushes them propagates at velocities that make any mechanical process seem frozen. This is how intercontinental phone calls can happen in real time, how the internet can connect people on opposite sides of the planet with delays measured in milliseconds, how the modern world has effectively shrunk to the size of a single room despite the thousands of miles that separate its inhabitants. Electricity demonstrated to humanity that speed far beyond our experience was not merely possible, but harnessable, controllable, useful. Beyond our atmosphere, objects move at speeds that make lightning seem almost pedestrian. Meteors, those streaks of light that flash across the night sky during annual showers and random encounters, enter Earth's atmosphere at velocities ranging from 25,000 to 160,000 miles per hour. The lower end of this range represents objects that were essentially keeping pace with Earth as it orbits the Sun, overtaken from behind like a faster car passing you on the highway. The upper end represents head-on collisions, objects traveling in the opposite direction around the Sun, their velocity and ours combining into a closing speed that creates tremendous kinetic energy upon impact with the atmosphere. This energy is what creates the bright streak you see, the meteor's surface vaporizing from friction with air molecules, glowing with heat as it decelerates from cosmic velocity to something the atmosphere can absorb. Most meteors are tiny, no larger than grains of sand, yet their tremendous speed gives them enough energy to create visible trails across dozens of miles of sky. The Chelyabinsk meteor that exploded over Russia in 2013 entered the atmosphere at about 42,000 miles per hour, and despite being only about 60 feet across, it released energy equivalent to 500,000 tons of TNT when it detonated. No explosive was involved, only speed. The kinetic energy of a modest rock traveling at cosmic velocity exceeded many nuclear weapons. This is the power of speed, the terrible mathematics of mass and velocity combining to create destruction that dwarfs anything chemistry can achieve. Comets demonstrate what happens when objects fall toward the Sun from the outer reaches of the solar system. A comet in the distant Oort cloud drifts at only a few hundred miles per hour, barely moving by cosmic standards. But as it falls inward toward the Sun, gravity accelerates it constantly, adding velocity with every mile of its journey. By the time a comet reaches the inner solar system, it may be traveling at 100,000 miles per hour. By the time it swings around the Sun at closest approach, that speed can exceed 1 million miles per hour for the most extreme sun-grazing comets. This is the same gravitational acceleration that the Parker Solar Probe exploits, the same cosmic mechanism that nature has been using to accelerate objects since the solar system formed 4.5 billion years ago. Comets are natural speedsters, falling toward the Sun at velocities that no rocket could match, their tails streaming behind them as solar radiation pushes dust and gas away from their icy surfaces. Many comets don't survive their close encounters with the Sun, vaporized completely by the intense heat or torn apart by tidal forces. But those that do emerge travel at speeds that seemed impossible to early astronomers, proof that the cosmos operates on scales of velocity that dwarf anything we experience on Earth. The speeds we've explored so far, from walking pace to meteor velocity, all occur within the tiny sphere of our solar system, a region that occupies less than a trillionth of the Milky Way galaxy's volume. To find truly extreme speeds, we need to expand our view to encompass the galactic stage, where stars orbit a central black hole, where hypervelocity objects race toward intergalactic space, and where the remnants of dead stars spin at rates that blur the line between matter and light. The Earth beneath your feet, so solid and stationary seeming, is actually hurtling through space at about 67,000 miles per hour as it orbits the Sun. You don't feel this motion because everything around you moves together. The atmosphere, the oceans, the buildings, all sharing the same velocity, and therefore appearing stationary relative to each other. But from the perspective of the Sun, you are racing around a nearly circular track at speeds that would vaporize any vehicle attempting to match them through atmosphere. In the time it takes you to read this paragraph, you've traveled roughly 100 miles through space, orbiting a star that doesn't even notice your presence. Mercury, the closest planet to the Sun, orbits even faster, racing around its tight elliptical path at about 107,000 miles per hour. This higher speed is a direct consequence of Mercury's proximity to the Sun, the same gravitational mathematics that accelerates comets and will accelerate the Parker Solar Probe. The closer you are to a massive object, the faster you must travel to maintain orbit, otherwise you fall inward and eventually collide. Mercury's year lasts only 88 Earth days, precisely because of this relationship between orbital distance and velocity. The planet completes more than 4 orbits around the Sun for every single orbit Earth completes, racing through its year while we're still in our first season. Jupiter's moons demonstrate the same principle in miniature, with innermost Io whipping around the giant planet at about 38,000 miles per hour, its orbit so tight and fast that Jupiter's immense gravity heats its interior through tidal flexing, creating the most volcanically active body in the solar system. But even these planetary speeds are modest compared to what we experience as passengers on a much larger journey. The entire solar system, sun and planets and comets and all, orbits the center of the Milky Way galaxy at approximately 515,000 miles per hour. We are falling around a supermassive black hole, 4 million times the mass of our Sun, held in orbit by gravity across a distance of 26,000 light-years. At this tremendous speed, you might expect that we complete galactic orbits fairly quickly, but the Milky Way is so vast that even at 500,000 miles per hour, one complete orbit takes about 225 to 250 million years. The last time our solar system occupied its current position in the galaxy, dinosaurs had not yet evolved. Earth was in the Triassic period, dominated by early reptiles and primitive mammals. Since then, the dinosaurs rose to dominance, ruled the planet for over 160 million years, perished in a mass extinction, and were replaced by mammals that eventually produced humans who built civilizations and looked up at the stars, wondering about their place in the cosmos. All of human history, all of civilization, all of recorded time represents a tiny arc of a single galactic orbit, a brief moment in a journey that has been ongoing for billions of years and will continue for billions more. Most stars in the galaxy move at similar speeds, orbiting the galactic center in a vast pinwheel of stellar motion. But some stars move much faster, accelerated to velocities that will eventually carry them out of the galaxy entirely. These hypervelocity stars travel at 1 to 4 million miles per hour relative to the galactic center, fast enough to escape the Milky Way's gravitational pull and drift into the void between galaxies. How does a star achieve such tremendous speed? The most common mechanism involves a close encounter with the supermassive black hole at the galaxy's heart. When a binary star system, two stars orbiting each other, falls toward this cosmic monster, tidal forces can rip the pair apart. One star is captured by the black hole, doomed to spiral inward, while the other is flung away at tremendous velocity, like a stone released from a sling. This gravitational slingshot effect can accelerate stars to speeds that would be impossible through any other mechanism, converting the energy of the infalling companion into kinetic energy of the escaping star. The fastest known star, designated S5HVS1, travels at roughly 4 million miles per hour, ejected from the galactic center about 5 million years ago. It has already traveled far from its birthplace and will eventually leave the Milky Way entirely, destined to wander the intergalactic void for eternity. Neutron stars represent perhaps the most extreme example of stellar speed, not through motion across space, but through rotation. When a massive star explodes as a supernova, its core collapses into an incredibly dense remnant only about 12 miles across, but containing more mass than our Sun. Conservation of angular momentum means that any rotation the original star possessed becomes enormously amplified as it shrinks, like an ice skater pulling in her arms to spin faster. Some neutron stars rotate hundreds of times per second, their surfaces moving at significant fractions of the speed of light. The fastest known pulsar, PSR J1748-2446 AD, spins 716 times every second, its equator moving at about 24% of light speed. If it rotated much faster, it would tear itself apart, the centrifugal force at its surface exceeding the gravitational force holding it together. These spinning remnants emit beams of radiation that sweep across the cosmos like lighthouse beacons, detectable from thousands of light years away, as regular pulses of radio waves. When pulsars were first discovered in 1967, their clockwork regularity led some astronomers to briefly wonder if they might be signals from extraterrestrial civilizations. The reality turned out to be even more extraordinary. The spinning corpses of dead stars, rotating at speeds that blur the boundary between the possible and the impossible, marking time across the galaxy with metronomic precision. Everything we've discussed so far, from walking speed to hypervelocity stars to spinning neutron stars, operates within a realm that physics can describe without too much strangeness. The speeds are extreme by human standards, certainly, but they don't fundamentally challenge our intuitions about how the universe works. Stars orbit galaxies, planets orbit stars, and objects follow predictable paths through space at velocities that seem reasonable given the forces involved. But now we must venture into territory where physics becomes genuinely strange, where objects move so fast that Einstein's theories of relativity transform from abstract mathematics into concrete reality. We must examine the universe's most powerful accelerators, cosmic engines that put anything humans have ever built to shame, mechanisms that have been pushing particles toward the ultimate speed limit for billions of years. These accelerators don't exist in laboratories or research facilities. They exist at the hearts of galaxies, in the remnants of exploded stars, in the most violent events the cosmos can produce. And they create objects moving so fast that time itself begins to warp around them. At the center of many galaxies lurks a supermassive black hole, a gravitational monster containing millions or billions of times the mass of our Sun compressed into a region smaller than our solar system. When matter falls towards such a black hole, it doesn't simply disappear quietly into the event horizon. Instead, it forms an accretion disk, a swirling vortex of gas and dust spiraling inward at tremendous speeds, heated by friction and compression to temperatures of millions of degrees. The accretion disk glows with the fury of this infalling matter, outshining entire galaxies in some cases. But the accretion disk is not the most remarkable feature of these systems. Something even more extraordinary emerges from the chaos. Jets. Perpendicular to the accretion disk, narrow beams of particles shoot outward at velocities approaching the speed of light. These jets can extend for thousands or even millions of light years, far beyond the boundaries of the galaxies that produce them, representing some of the largest coherent structures in the entire universe. The mechanism that creates these jets is still not fully understood, despite decades of study. Somehow, the combination of intense magnetic fields, the rotation of the black hole itself, and the dynamics of the accretion disk conspire to accelerate particles to relativistic velocities and focus them into tight beams that punch through intergalactic space like cosmic searchlights. The particles within these jets move at 90 to 99% of the speed of light, velocities so extreme that the effects predicted by Einstein's special relativity become dramatically apparent. Time passes more slowly for these particles than for stationary observers. Their mass effectively increases as they approach light speed. The very concepts of distance and duration become warped and transformed. These are not subtle effects, measurable only with precise instruments. At 99% of light speed, time passes about 7 times more slowly for the moving particle than for someone watching from outside. At 99.9%, time slows by a factor of about 22. The faster you go, the more dramatically these effects manifest, asymptotically approaching infinity as you approach the speed of light itself. The jets from supermassive black holes are natural laboratories for relativistic physics, demonstrating effects that Einstein predicted over a century ago on scales that dwarf anything humans could ever construct. When one of these jets happens to point directly at Earth, we observe what astronomers call a blazar. We are looking straight down the barrel of a cosmic particle cannon, seeing the jet face on rather than from the side. This viewing angle creates remarkable effects. The light from the jet appears dramatically brighter than it would from any other angle, a phenomenon called relativistic beaming. The blazar outshines everything else in its host galaxy, sometimes by factors of thousands. Not because it produces more light, but because that light is concentrated in our direction by the geometry of relativistic motion. Blazars are among the brightest objects in the known universe, visible across billions of light years, beacons marking the locations of supermassive black holes whose jets happen to aim our way. Some blazars display a phenomenon that seems to violate physics itself. Components within their jets appear to move faster than the speed of light. Astronomers have measured jet features separating at apparent velocities of 5, 10, even 20 times light speed. This superluminal motion puzzled scientists when it was first observed, seemingly contradicting everything Einstein had established about cosmic speed limits. But the explanation, once understood, reveals the strangeness of relativistic physics rather than any violation of it. When something moves toward you at nearly light speed, at a small angle to your line of sight, the light from different positions along its path arrives at almost the same time. This compression of arrival times creates an optical illusion where the object appears to move faster than it actually does. Nothing is exceeding light speed. The geometry of space-time at relativistic velocities simply plays tricks on our perception. Even more extreme than the steady jets of blazars are gamma-ray bursts, the most powerful explosions in the universe since the Big Bang itself. These cataclysmic events occur when massive stars collapse into black holes, or when neutron stars collide and merge. In the moment of collapse or collision, jets of particles are launched at velocities even more extreme than those from galactic black holes. The material in gamma-ray burst jets moves at 99.99% of light speed or faster, with some estimates suggesting velocities of 99.999% of light speed in the most extreme cases. At these velocities, time for the particles passes thousands of times more slowly than time for distant observers. The particles experience crossing vast cosmic distances in what feels to them like mere moments, while we observe their journey taking years or centuries. A gamma-ray burst releases more energy in a few seconds than our sun will produce in its entire 10 billion-year lifetime. If one occurred within a few thousand light-years of Earth and its jet pointed our way, the radiation would strip away our ozone layer and potentially trigger a mass extinction. Fortunately, such nearby events are extremely rare, but they demonstrate the sheer power that cosmic acceleration can achieve. The jets from black holes and gamma-ray bursts accelerate enormous quantities of matter to relativistic speeds, vast streams of particles flowing through space like cosmic rivers of energy. But when we search for the absolute fastest objects ever detected, we must narrow our focus from these bulk flows to individual particles, single atomic nuclei that have been accelerated to velocities so extreme they defy comprehension. These particles are called cosmic rays, though the name is somewhat misleading. They are not rays at all, not beams of light or electromagnetic radiation, but rather individual protons, helium nuclei, and occasionally heavier atomic nuclei traveling through space at nearly the speed of light. They bombard Earth constantly, about 10,000 of them striking every square meter of our atmosphere every second, a ceaseless rain of high-speed particles that has been falling since our planet formed. Most cosmic rays are relatively modest in energy, deflected by Earth's magnetic field or absorbed by our atmosphere long before they reach the surface. But some carry energies so extreme that they represent the fastest individual objects ever observed by human instruments. Cosmic rays were discovered in 1912 by an Austrian physicist named Victor Hess, who carried radiation detectors aboard a balloon flight to high altitude. The prevailing assumption at the time was that radiation decreased with altitude, since it was thought to originate from radioactive materials in the Earth's crust. Instead, Hess found that radiation increased as he ascended, reaching levels several times higher at 16,000 feet than at ground level. Something was irradiating the atmosphere from above, from space itself. Hess correctly concluded that high-energy particles from beyond Earth were constantly bombarding our atmosphere, a discovery that earned him the Nobel Prize in Physics in 1936. In the century since Hess's discovery, we have learned that cosmic rays span an enormous range of energies. The lowest energy cosmic rays are relatively gentle, easily deflected by planetary magnetic fields and absorbed by thin layers of atmosphere. Higher energy particles punch deeper, creating cascades of secondary particles as they collide with atmospheric molecules. The highest energy cosmic rays, the ones that concern us tonight, carry so much energy that they create showers of billions of secondary particles that spread across miles of atmosphere, detectable by arrays of sensors on the ground. The energy scale of cosmic rays extends across more than 12 orders of magnitude, from particles comparable to those produced in human accelerators, to particles millions of times more energetic than anything we can create. The Large Hadron Collider, the most powerful particle accelerator ever built by humanity, accelerates protons to energies of about 6.5 trillion electron volts. This is sufficient to probe the fundamental structure of matter, to discover particles like the Higgs boson, to explore physics at scales far smaller than atoms. And yet the highest energy cosmic rays carry energies of more than 100 million trillion electron volts, roughly 40 million times what the Large Hadron Collider can achieve. No facility humans could conceivably build would match the acceleration power that nature routinely achieves. The cosmos is a particle physicist's laboratory of unlimited budget and unlimited scale, running experiments that dwarf our greatest technological achievements. On October 15, 1991, a detector array in the Utah desert called Fly's Eye observed something extraordinary. A single cosmic ray particle triggered sensors across a wide area, its shower of secondary particles revealing an energy of 320 ex-electron volts. Written out in full, that's 320 billion electron volts, or about 320 quintillion electron volts in American notation. The scientists analyzing the data reportedly exclaimed in disbelief when they calculated the energy, and the particle became informally known as the "Oh my God" particle. This single proton, a particle so small that trillions of them could fit on the head of a pin, carried the kinetic energy of a baseball thrown at 60 miles per hour. All the energy of a macroscopic object moving at significant speed, concentrated in a single subatomic particle. The difference between its speed and light speed was so small as to be almost meaningless, yet that infinitesimal difference represents a barrier that no massive object can ever cross. To appreciate how close this particle was to light speed, consider the following thought experiment. Imagine racing the "Oh my God" particle against a photon, a particle of light traveling at exactly the cosmic speed limit. Start them side by side and let them race across the entire observable universe, a distance of 93 billion light-years. After this inconceivable journey, spanning distances that light itself requires billions of years to traverse, the photon would win by approximately 46 feet. 46 feet. After 93 billion light-years of travel, the "Oh my God" particle was so close to light speed that the difference was essentially philosophical rather than practical. A testament to how effectively cosmic accelerators can push matter toward the ultimate limit while never quite achieving it. The "Oh my God" particle and its extreme cousins raise a profound question that sits at the heart of modern physics. Why is there a cosmic speed limit at all? Why can't particles simply continue accelerating forever, gaining velocity without bound until they reach speeds that make even 99.999% of light speed seem slow? The answer lies in the fundamental structure of space-time itself, in insights that Albert Einstein published in 1905 that transformed our understanding of reality more profoundly than perhaps any other scientific discovery in history. Before Einstein, physicists assumed that space and time were separate and absolute. Space was the stage on which events occurred, unchanging and uniform throughout the universe. Time was the cosmic clock that ticked at the same rate for everyone, everywhere, regardless of their motion or location. Speed was simply distance divided by time, and there was no theoretical reason why anything couldn't travel at any speed whatsoever. If you had a powerful enough engine and enough fuel, you could accelerate forever, eventually reaching speeds of millions or billions of times the speed of light. Nothing in the physics of Isaac Newton prohibited such velocities. Einstein's special theory of relativity demolished these intuitions with elegant mathematical precision. He began with a simple observation that had puzzled physicists for decades. The speed of light in a vacuum appeared to be the same for all observers, regardless of how they were moving relative to the light source. This seems counterintuitive at first. If you're standing on a platform and a train passes at 60 miles per hour, the train appears to move at 60 miles per hour relative to you. But if you're on another train moving at 30 miles per hour in the same direction, the first train appears to move at only 30 miles per hour relative to you. Velocities add and subtract based on relative motion. This is how the everyday world works, but light doesn't follow these rules. Whether you're standing still, moving toward a light source, or moving away from it, you always measure the same speed of light. 299,792,458 meters per second. Exactly. This constancy is not a quirk or an approximation. It appears to be woven into the fundamental fabric of reality. To make sense of this strange observation, Einstein realized that our intuitions about space and time must be wrong. If the speed of light is constant for all observers, then something else must be variable to compensate. That something turns out to be time itself, along with space and mass. When you move relative to another observer, time passes at different rates for each of you. Space contracts along your direction of motion. Your mass effectively increases as you gain velocity. These effects are imperceptible at everyday speeds, far too small to notice when you're driving a car or flying in an airplane. But as you approach the speed of light, they become dramatic and eventually dominant. Time for a fast-moving object passes more slowly than time for a stationary observer. This is not an illusion or a measurement error. It is a fundamental feature of reality, confirmed by countless experiments over the past century. Atomic clocks flown on airplanes tick slightly slower than identical clocks on the ground. Particles created in accelerators live longer than identical particles at rest because time passes more slowly for them. GPS satellites must account for relativistic time dilation to provide accurate positioning, adjusting their clocks to compensate for the effects of their orbital velocity. The implications for cosmic speed become clear when you consider what happens as an object approaches light speed. The energy required to accelerate an object depends on its mass, and as the object moves faster, its effective mass increases. At half the speed of light, the mass increase is modest, about 15%. At 90% of light speed, the mass has more than doubled. At 99%, it has increased by a factor of about 7. At 99.9%, by a factor of about 22. At 99.9%, by a factor of about 70. The pattern continues asymptotically, the mass increase growing without bound as velocity approaches the speed of light. At light speed itself, the mass would be infinite, and infinite mass would require infinite energy to accelerate. This is why nothing with mass can ever reach light speed. Not because of engineering limitations, not because we haven't built powerful enough engines, but because the very structure of space-time makes it impossible. The speed of light is not merely very fast, it is the maximum rate at which causality can propagate, the ultimate speed limit embedded in the fabric of existence. The particle's effective mass was roughly 300 billion times greater than its rest mass, transformed by velocity from a tiny proton into something carrying the kinetic energy of a thrown baseball. And yet, even with all that energy, even after being accelerated by the most powerful natural processes the universe can produce, it still fell infinitesimally short of light speed. That tiny gap, that difference of less than a trillionth of a percent, represents an unbridgeable chasm. You could pour all the energy in the observable universe into accelerating a single proton, and it would still never quite reach light speed. The asymptote cannot be crossed. For the oh my God particle itself, if we could somehow imagine its perspective, the universe would appear radically transformed. Time dilation at such extreme velocities means that time for the particle passes about 300 billion times more slowly than time for us. 1 second of the particle's experience corresponds to roughly 9,500 years of our time. The particle could cross the entire Milky Way galaxy, a journey that takes light itself 100,000 years, in what the particle would experience as about 20 minutes. From the particle's reference frame, the galaxy would appear compressed along its direction of travel, squashed by length contraction into a pancake only a few light hours thick, rather than 100,000 light-years across. The universe the particle inhabits is utterly different from the universe we experience, transformed by velocity into something almost unrecognizable. These are not theoretical speculations, but direct consequences of physics that has been tested and confirmed countless times. The oh my God particle genuinely experienced crossing cosmic distances in what felt like moments, even as billions of years passed in the rest of the universe. If nothing can exceed the speed of light, how do we explain observations that seem to show exactly that? Astronomers have measured jet components in distant blazars, separating at apparent speeds of 5, 10, even 20 times the speed of light. Galaxies at the edge of the observable universe are receding from us faster than light itself travels. Quantum mechanics describes instantaneous correlations between particles separated by any distance. Each of these phenomena appears to violate Einstein's cosmic speed limit, yet none of them actually does. Understanding why these apparent violations are not real violations reveals just how subtle and counterintuitive relativistic physics can be, and reinforces rather than undermines the absolute nature of the light-speed barrier. The superluminal motion observed in blazar jets is perhaps the most visually striking apparent violation of relativity. When astronomers photograph these jets over months or years, they can track individual features moving outward from the central black hole. In some cases, these features appear to separate at velocities several times the speed of light. The effect is real in the sense that it's what we actually observe, but it's an optical illusion created by the geometry of relativistic motion. When an object moves toward you at nearly light speed, at a small angle to your line of sight, the light emitted from different points along its path arrives at almost the same time. The object is chasing its own light, nearly keeping pace with the photons it emits. This compression of arrival times makes the object appear to cover more distance per unit time than it actually does. A jet component moving at 98% of light speed at an angle of 10 degrees to our line of sight would appear to move at about 3.5 times light speed. At 99% and 5 degrees, it would appear to move at about 10 times light speed. No actual velocity exceeds light speed. The jet material is always moving below the cosmic limit, but the geometry of observation creates an illusion of superluminal motion that fooled astronomers when it was first observed and required years of theoretical work to fully explain. The recession of distant galaxies faster than light is a different phenomenon entirely, one that reveals the expansion of space itself rather than motion through space. The most distant galaxies we can observe are receding from us at roughly 3 times the speed of light. Their light, already ancient when it began its journey, has been traveling toward us for billions of years, while the space it traverses has been continuously expanding. By the time the light reaches us, the galaxy that emitted it has moved far beyond the distance that light could have traveled in the same time. This seems paradoxical until you understand the distinction between motion through space and expansion of space. The galaxies are not traveling through space at superluminal velocities. They are essentially stationary in their local region of space. But space itself is expanding, creating new distance between us and them faster than light can traverse that distance. Einstein's speed limit applies to motion through space, not to the expansion of space itself. The fabric of the universe plays by different rules than objects moving upon that fabric. Perhaps the strangest apparent violation of the light speed limit comes from quantum mechanics, in the phenomenon known as entanglement. When two particles become entangled through quantum interactions, measuring a property of one particle instantaneously determines the corresponding property of the other particle, regardless of how far apart they are. Einstein famously called this spooky action at a distance and was deeply troubled by its implications. If measuring one particle instantly affects another particle across the universe, doesn't that represent faster than light communication? The answer, which took decades of theoretical and experimental work to establish, is no. Entanglement creates correlations between measurements, but it cannot be used to transmit information. When you measure an entangled particle, you get a random result. Your measurement does affect the distant particle, but you have no control over what that effect is. To confirm that entanglement has occurred, you must compare your results with the distant observer's results, and that comparison can only happen through conventional communication channels that respect the light speed limit. Entanglement is genuinely strange, a feature of quantum mechanics that defies classical intuition, but it does not violate causality or allow faster-than-light signaling. Theoretical physicists have occasionally explored the mathematics of hypothetical particles that always travel faster than light, never slower. These particles, called tachyons, would exist on the other side of the light speed barrier, unable to slow down to light speed just as ordinary particles cannot speed up to it. Tachyons are mathematically consistent in some formulations, but they would create severe problems for causality. A tachyon emitted from Earth could arrive at a distant star before a beam of light emitted at the same time. Under certain reference frames, this would mean the tachyon arrived before it was emitted, effect preceding cause, opening the door to paradoxes that would undermine the logical structure of the universe. No experimental evidence for tachyons has ever been found, despite decades of searching. Most physicists believe they do not exist, that the speed of light is a genuine barrier in both directions, preventing ordinary matter from speeding up to light speed and preventing hypothetical faster-than-light matter from slowing down to it. The cosmic speed limit appears to be absolute and inviolable, enforced not by any physical mechanism but by the fundamental geometry of space-time. The apparent violations of light speed we observe all turn out, upon careful analysis, to reinforce rather than undermine Einstein's insights. Superluminal motion in jets is an optical illusion. Galactic recession involves expanding space, not superluminal motion through space. Quantum entanglement creates correlations without communication. Tachyons remain hypothetical and probably non-existent. The speed of light stands as an absolute limit, the cosmic boundary that cannot be crossed regardless of how much energy you apply or how clever your engineering becomes. The oh my god particle, with all its tremendous energy, still fell infinitesimally short of this limit. Nothing ever detected has exceeded it. Nothing ever will. Throughout this journey from walking pace to the fastest particles ever detected, we have been observers, witnesses to speeds achieved by nature through processes that operate on scales far beyond human control. Comets fall toward the sun because gravity compels them. Stars orbit the galactic center because the mass distribution of the Milky Way dictates their paths. Cosmic rays achieve their tremendous velocities through shock waves and magnetic fields that have been operating since before Earth existed. But humans have not been content merely to observe cosmic speed. We have pursued it ourselves, building machines of increasing sophistication in our quest to accelerate particles to velocities that approach the cosmic limit. This pursuit has consumed billions of dollars, occupied thousands of brilliant minds, and produced some of the most remarkable engineering achievements in human history. And yet, for all our effort, for all our ingenuity, we remain far behind what nature achieves routinely through violence and time. The Large Hadron Collider, built by the European Organization for Nuclear Research beneath the border between Switzerland and France, represents the pinnacle of human acceleration technology. This machine is a ring 17 miles in circumference, buried hundreds of feet underground to shield it from cosmic ray interference and to contain its operations away from surface disruptions. Within this ring, protons are accelerated to 99.99991% of the speed of light, circling the tunnel 11,000 times every second as superconducting magnets cooled to temperatures colder than outer space bend their paths into a continuous loop. The protons travel in two beams moving in opposite directions, and at designated collision points, these beams are crossed, allowing protons to smash into each other at combined energies sufficient to probe the fundamental structure of matter. The discovery of the Higgs boson in 2012, the particle that gives other particles their mass, vindicated decades of theoretical work and billions of dollars of investment. The Large Hadron Collider has peered deeper into the subatomic realm than any instrument before it, revealing secrets of the universe that would have remained forever hidden without such extreme velocities. And yet the Large Hadron Collider's achievements, remarkable as they are, pale against what cosmic accelerators accomplish. The protons in the LHC carry energies of about 6.5 trillion electron volts, enough to create new particles through the conversion of kinetic energy into mass, according to Einstein's famous relationship. The oh my god particle carried energy of 320 quintillion electron volts, roughly 40 million times greater. To match this energy with human technology, we would need to build an accelerator, not 17 miles in circumference, but hundreds of millions of miles, a ring larger than Earth's orbit around the Sun. Such a machine is not merely beyond current engineering capabilities. It is beyond any engineering capabilities we can plausibly imagine for centuries to come. nature builds accelerators of unlimited scale, using magnetic fields that stretch across light years and shock waves that propagate for millions of years. We build accelerators, constrained by budgets and land availability and political will. Impressive by human standards, but trivial by cosmic ones. The pursuit of speed extends beyond particle physics into the realm of space travel, where the challenge is not merely to accelerate particles, but to accelerate spacecraft carrying instruments, and perhaps someday humans, to velocities that might make interstellar travel feasible. The Voyager probes, launched in 1977, travel at about 38,000 miles per hour, a speed that sounds impressive until you calculate that reaching the nearest star at this velocity would require over 70,000 years. The New Horizons mission to Pluto travels slightly slower, the Parker Solar Probe slightly faster. None of these spacecraft approach even 1% of 1% of the speed of light. At current propulsion technology, reaching another star within a human lifetime is impossible. The distances are simply too vast, and our engines are simply too weak. Visionary projects have proposed ways to dramatically increase spacecraft velocity. The Breakthrough Starshot Initiative, funded by technology billionaires and supported by prominent physicists, envisions tiny spacecraft weighing only grams, accelerated by powerful ground-based lasers to 20% of the speed of light. At this velocity, a probe could reach Alpha Centauri, the nearest star system, in about 20 years, transmitting data back across the 4 light-year distance for another 4 years before results arrived on Earth. 20% of light speed would be by far the fastest any human-made object has ever traveled, thousands of times faster than our current spacecraft. But even this ambitious goal, if achieved, would still leave us far behind the cosmic rays that bombard Earth daily. 20% of light speed is impressive for human engineering, but modest compared to the 99.99999% achieved by the "oh my god" particle. The gap between what we can build and what nature routinely produces remains almost inconceivably vast. Perhaps more profound than the engineering challenges are the fundamental limitations that relativity imposes on our cosmic ambitions. Even if we could somehow accelerate a spacecraft to 99% of light speed, the journey to nearby stars would still take years from the perspective of observers on Earth. Time dilation would help the travelers who would experience the journey as taking less time than stationary observers would measure. But communication with home would still be limited by the light speed barrier. A message sent from Alpha Centauri takes 4 years to reach Earth, regardless of how fast the spacecraft that carried the sender was traveling. Real-time communication across interstellar distances is impossible, not because of engineering limitations, but because of the fundamental structure of spacetime. Each spacecraft we send to the stars becomes increasingly isolated, increasingly alone, separated from humanity, not just by distance, but by the unbridgeable gap that light speed imposes on information transfer. The human pursuit of speed reveals something essential about our nature as a species. We are not content to accept limitations, not satisfied with being told that something cannot be done. When physicians warned that traveling at 30 miles per hour might kill passengers, engineers built faster trains. When aerodynamicists worried that the sound barrier was impenetrable, test pilots punched through it. When the distances to other planets seemed impossibly vast, rocket scientists designed missions that reached them anyway. This relentless drive to exceed boundaries has brought us from walking pace to orbital velocity in little more than a century, a transformation unprecedented in the history of life on Earth. But the light speed barrier is different from all previous barriers. It is not an engineering challenge to be overcome with sufficient cleverness. It is a fundamental feature of reality, woven into the mathematical structure of the universe at the deepest level. No amount of innovation, no breakthrough in propulsion technology, no discovery of new physics will allow massive objects to exceed light speed. This is the wall we cannot climb, the barrier that defines the ultimate limit of motion. We have climbed the ladder of velocity from its lowest rungs to its highest. At each step, the previous speed seemed to freeze in comparison, motion becoming stillness as we ascended to the next level. The fastest human sprint became stationary compared to automobiles, supersonic aircraft became frozen compared to spacecraft. Even the sun's orbital velocity around the galaxy became negligible compared to the particles accelerated by cosmic violence. And at the top of the ladder, pressing against the cosmic speed limit itself, we found objects moving so fast that the difference between their velocity and light speed could only be expressed in streams of nines after a decimal point. The fastest objects ever detected by human instruments are individual atomic nuclei, cosmic rays accelerated over millions of years by processes we still don't fully understand, carrying the kinetic energy of macroscopic objects in packages smaller than atoms. What does this journey through the realm of speed tell us about the universe we inhabit? First, it reveals that the cosmos operates on scales that dwarf human experience in every dimension. Not just size and time, but velocity as well. The speeds we encounter in daily life, the speeds that feel fast and exhilarating to our nervous systems, evolved on the African savanna, represent the tiniest fraction of what is possible. Even our most sophisticated technology, our most powerful accelerators and fastest spacecraft barely scratch the surface of cosmic capability. We are slow creatures in a fast universe, limited by bodies that would be destroyed by the accelerations necessary to approach relativistic velocities, constrained by lifespans too short to complete interstellar journeys at the speeds we can currently achieve. The universe's speed limit is approximately 670 million miles per hour, and we have achieved roughly 1/1600th of that with our best spacecraft. Second, this journey reveals the profound unity of space, time, and energy that Einstein's relativity describes. Speed is not merely distance divided by time, a simple ratio with no deeper significance. Speed determines the rate at which time passes, the length of objects, the effective mass of particles. The faster you move through space, the slower you move through time. At light speed, time stops entirely. Distance in the direction of motion contracts to zero, and mass becomes infinite. These are not abstract mathematical curiosities, but concrete features of reality that cosmic rays experience and that our particle accelerators confirm with every experiment. The universe does not separate space and time into independent dimensions, but weaves them together into a unified fabric called space-time. And motion, through this fabric, has consequences that Newton never imagined. Third, this journey confronts us with limits that cannot be transcended. Throughout human history, every barrier we encountered eventually fell to determination and ingenuity. Mountains were crossed, oceans were navigated, the sky was conquered, the atom was split. We have internalized the lesson that no obstacle is truly insurmountable, that given enough time and effort, any challenge can be overcome. But the speed of light is different. It is not a barrier erected by circumstance or insufficient technology. It is a boundary built into the mathematical structure of existence, as fundamental as the fact that triangles have 3 sides or that 2 + 2 = 4. The oh my God particle, accelerated by the most powerful natural processes the universe can produce, driven by energies we cannot replicate, still fell infinitesimally short of light speed. Nothing we can ever build, no discovery we can ever make, will allow us to exceed this limit. For a species accustomed to breaking barriers, this confrontation with an absolute boundary is both humbling and clarifying. And yet there is beauty in this limitation. The speed of light does more than constrain our motion. It protects causality, ensuring that effects follow causes in a logical sequence that makes the universe comprehensible. Without this cosmic speed limit, faster-than-light particles could carry information backward in time, creating paradoxes that would undermine the very possibility of understanding. The same barrier that traps us within our local region of space also preserves the logical structure of reality, ensuring that the universe makes sense, that science is possible, that knowledge can accumulate and build upon itself. The speed of light is not merely a limit, but a guardian, protecting the order without which consciousness could not exist. When you look up at the night sky tonight, consider what you now know about cosmic speed. The light reaching your eyes from distant stars travels at the ultimate velocity, the cosmic speed limit that nothing can exceed. Somewhere out there, cosmic rays are racing through the void at 99.999% of that limit, individual protons carrying more energy than baseballs, crossing galaxies in what they experience as moments, while eons pass for the rest of the universe. Blazar jets are pumping streams of relativistic particles into intergalactic space, their apparent superluminal motion revealing the strange geometry of space-time at extreme velocities. Gamma-ray bursts are launching the fastest bulk flows of matter in the universe, explosions so powerful they briefly outshine entire galaxies. All of this violence, all of this speed, operates within the constraint of a single number: 299,792,458 meters per second, the speed at which causality propagates, the boundary between the possible and the forbidden. The Oh My God particle, detected on an October night in 1991 in the Utah desert, remains the fastest object ever recorded by human instruments. Its origin is still unknown, its source still mysterious. Somewhere in the cosmos, something accelerated a single proton to energies that would require us to build accelerators larger than planetary orbits to replicate. That particle traveled across the universe for millions or billions of years, experiencing the journey as mere moments due to the extreme time dilation of its velocity, before finally colliding with an atmospheric molecule above the Earth and showering secondary particles across the detector array. In that shower of particles, we glimpsed the extreme end of what motion can achieve, the ragged edge of the cosmic speed limit, the fastest anything has ever moved in the observable universe. And even that particle, with all its tremendous energy, with all the cosmic violence that produced it, still fell just barely short of the speed of light. The barrier held as it always has, as it always will. Speed has a limit, and we have seen objects pressing against it with all the fury the universe can muster, coming infinitely close, but never quite breaking through.